What makes pulsar timing in neutron stars so complicated? Imagine trying to listen to a perfectly ticking clock that sometimes skips a beat or speeds up without warning. That's what scientists face when they try to measure the pulses from neutron stars. These stars are the dense leftovers of massive stars that exploded as supernovae. They are incredibly small, about the size of a city, but contain more mass than our sun. They spin hundreds of times per second, sending beams of radio waves across space like cosmic lighthouse beacons. When these beams sweep past Earth, we detect pulses that are usually extremely regular, more precise than atomic clocks. But many things make timing these pulses a real challenge. First, even though pulsars are known for their steady rotation, they don't spin at exactly the same rate forever. Over time, they slow down because they lose energy through electromagnetic radiation. This gradual slowdown is called spin down, but it's not always smooth. Sometimes, the star's internal structure changes, causing tiny irregularities in how fast it spins. These small shifts can throw off the timing unless scientists carefully model and account for them. Second, the magnetic axis of a pulsar is usually tilted compared to its rotational axis. This tilt causes the beams of radiation to sweep across space in a specific pattern. If the magnetic axis shifts slightly or the star's rotation wobbles, the timing of the pulses can shift too. These small changes can make it tricky to keep track of the exact arrival time of each pulse. Third, many pulsars are part of binary systems, meaning they orbit around another star or white dwarf. As they move in their orbits, the pulses we see are affected by the Doppler effect, similar to how a siren sounds higher or lower as it moves toward or away from us. The gravity of the companion star also causes relativistic effects, like the Shapiro delay, where the pulses take a tiny longer path through curved spacetime. Correcting for these effects requires very precise calculations. Fourth, the space between stars isn't empty. It's filled with charged particles that make the radio signals slow down or scatter unpredictably. These variations in the interstellar medium can cause delays or distortions in the pulses, adding another layer of complexity. Scientists need to filter out these effects to see the pulsar's true timing behavior. Fifth, the way pulsars emit their signals isn't fully understood. Sometimes, the shape or strength of the pulses changes, making it harder to identify the exact moment they arrive. This variability can be caused by changes in the star's magnetic field or emission processes, which are still being studied. Finally, the instruments used to observe pulsars have their limits. Different telescopes and detectors have varying sensitivities, and noise or gaps in data collection can introduce errors. Achieving the level of precision needed to study these stars requires advanced technology and careful calibration. All these factors combined make pulsar timing a complex task, but it's also what makes studying pulsars so exciting. They help us test Einstein's theory of general relativity, measure the mass of stars, and even hunt for gravitational waves. Understanding these tiny, spinning cosmic clocks pushes the boundaries of science and technology, showing us just how intricate and fascinating our universe really is.